We will continue now our discussion on the interconnection techniques and stringing of solar cells. There are different ways to electrically interconnect a number of solar cells to produce a module. In the previous video, we discussed the interconnection of conventional crystalline silicon modules. In this video, we will focus on the interconnection techniques used for advanced crystalline silicon modules and the thin film technologies. Let's start with the new advanced approaches used for the interconnection of crystalline silicon-based modules. These new crystalline silicon modules can have integrated circuit technology, which requires more advanced fabrication steps with a very precise alignment. In the PV2X photovoltaic technologies course, we discussed several advanced concepts for crystalline silicon solar cells in detail. We discussed in depth how the different module architectures influence the solar cell parameters. In this video, we will take one of those advanced designs concepts as an example to demonstrate the difference in interconnection techniques. To that end, we will look at the wrap-through module design. For the emitter wrap-through technology, the emitter layer, which covers the whole front surface, is wrapped through the absorber layer to the rear side in a number of places. At the rear side, the emitter layer forms a contact through a metallization process. The positive back contact, or absorber contact, is positioned in strips along the backside. Here you can see the cross-sectional view of the emitter wrap-through solar cell configuration. We can gather from the figure that the main advantage of this concept is the almost total absence of metal grids at the front surface of the solar cells. This solar cell design, therefore, has a very limited shading losses and a larger active area. An example of a metal wrap-through module is the so-called pin-up module that was developed at the ECN in the Netherlands. The pin-up module or PUM design was inspired by a water lily and has a limited number of holes through the absorber layer, typically 9 or 16. These holes serve as a true ways for interconnection of the front side metallization to the rear side by using metal pins. In this way, bus bars at the front side are eliminated. This reduces shading losses to 2 or 3% and leads to an overall efficiency increase. The biggest difference is that the backside of this module, where both P and N-type contacts are located, can be fabricated in advance. The back sheet, which in crystalline silicon was just a plain piece of plastic, now has a printed circuit. The conductive backsheet then has to be carefully aligned with the silicon wafers. When aligned correctly, the printed circuit on the backsheet is connected to the P and N-type contacts in order to extract the current. With the pin-up module design, the current cell production chain can almost remain unchanged. Indeed, for a fully automated module production, only the series connection of cells needs to be changed. For the PUM design, the cells are glued to the printed circuit by means of a conductive adhesive. In principle, it is therefore possible to interconnect the individual cells in a module without loss in fill factor. For conventional manufacturing, the stress in the soldered joint causes an increase in series resistance, which decreases the fill factor. The PUM design changed our way of thinking about module design, including the module fabrication process and the development of new concepts and designs. Making thin film modules is very different from making modules based on crystalline silicon solar cells. The fabrication of modules with the crystalline silicon technology involves two distinct steps: the cell production and the cell interconnection. In thin film technology, instead, producing cells and modules cannot be separated from each other. The series connection of the thin film modules is established by laser scribing. To illustrate these laser scribing steps, we will look at this thin film solar cell deposited in a superstrate configuration. On top of a glass substrate, the transparent front electrode is deposited. Then the first laser scribed is performed, called P1. The wavelength of the laser is such that it is transmitted through the glass and absorbed by the front contact. The P1 laser scribing step evaporates the material and leaves a gap in the front contact. Then the photoactive layers are deposited on top of the front contact, creating a thin film and filling the gap left by the first laser scribe. After depositing the absorber layer, the second laser scribe, called the P2, is performed. The wavelength of the laser has to be chosen in this case such that it is not absorbed by the glass and the transparent front contact, but in the absorber layer. The P2 laser scribe leaves a gap in the absorber layer. This gap is filled with the deposition of the final layer, which is the metallic back contact. Then the third laser scribe, called the P3, is performed. The wavelength of this laser scribe has to be chosen such that it is transmitted through all the preceding layers and is only absorbed by the back contact. It may therefore be, for instance, infrared light. The final laser scribe evaporates the metal and creates a gap in the back contact. Generally, the laser scribes run along the full length of the substrate module. We therefore end up with a module that consists of many very narrow cells of about 1 centimeter width and a length equal to the module length. If we zoom out, we can see how the current flows through the P2 scribe and connects the individual cells in series. The area in which the laser scribes take place is called the interconnect width. The cell width is therefore defined by the P3 and P1 scribes. Let's look also at the fabrication of a thin film CIGS module. First, the molybdenum back contact is deposited on top of the glass substrate. After the P1 laser scribe creates gaps in the back contact, the CIGS p-doped layer is deposited. The deposition of the CIGS absorber is followed by the P2 laser scribe and the deposition of the cadmium sulfide n-doped layer. The front tissue is deposited last. The last laser scribe divides the single CIGS solar cell as shown in figure. Here we can recognize the total cell area and the active area, which does not include the region that does not contribute to the current generated by the module. Naturally, the active area with respect to the total cell area should be as large as possible in order to maximize PV module performance. The issues related to monolithic integration are, for example, the fact that the laser scribes are performed in different steps during the production and therefore often with different machines. Further, the distance between the scribes might be different at different processes when they are performed at different temperatures. Aligning the glass plates in all the production steps is also extremely important for manufacturing high-quality thin film modules. To conclude, in the previous video we have seen how to fabricate a module with the conventional crystalline silicon wafers by means of series and parallel interconnections. In this video, we introduced the interconnection in some advanced design concepts like emitter wrap-through and metal wrap-through modules. Finally, we discussed the monolithic integration techniques used for the interconnection of thin film solar cells.